All right, so let's talk about this one, classification. And so what we're going to do is download these MNIST numbers. And what these are handwritten numbers from the U.S. Census. And they are labeled, and so we get to see various numbers that humans have written down and how they be. We're going to train an AI to turn them into computer read digits. So this is going to show the shape of the data. Okay, there it is, telling you about the database of handwritten digits and so on. And here's what it is. Here's what the data looks like. Just a series of numbers, which is 784 grayscale values that go from 0 to 255. And there's 70,000 images. Each one of them has 784 features, which are those pixels. And here's the labels. The first one's a 5, the next one's a 0, the next one's a 4, and so on. So this is labeled data, so we can do supervised learning on it. And here's how we view some of the images to see what it's going to be like. So we go here. And this will print, I'm not sure how many, but anyway, it'll print some of the data so we can see it. There we are. So that's what the data looks like. These numbers. By the way, this is kind of horrible. There's an artifact of the edges being cut off here, but anyway, that's the numbers with various kinds of defects. So now we've split it into training and testing sets. We'll take the first 60,000 as the training set, and then the remainder, which I think is 10,000, will be the test set. So there you go. Okay.
Sam, when I did this, I ended up putting in the length of the total data set to find out it was 70. I was confused about what it was doing.
Up here at 70. Now here's where you find the length. This part up here shows you the shape. This is 70,000 instances with 784 values in each dimensions.
Where do you see the 7? Oh, there it is.
Yeah.
Thank you. I missed that.
Yeah, and 784 is from 28 by 28. It's 28 by 28 pixel images. All right. So now we're gonna simplify the problem. You would like to sort it into 10 categories, but for now we're going to make a binary classifier that just sorts things into yes and no. So what we're going to do is we're going to just determine whether it's 5 or not 5. This is the simplest kind of classifier to make to get started. We'll do classifiers with more categories later. So I'm going to take the label, which was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'm going to create another thing that is just whether it's equal to 5 or not. So now we're going to get a training set, and the training set has 5,000 that are true and 50,000 that are false, because only 1/10 of them are 5s, of course. And the test set has 800 that are true and 9,000 that are false. So that's the new training and test set we're going to use. And now we can make a linear model. So you put in the image, you break out the pixels, and then you feed them into a neuron. And here's the classifier. And I think don't even have a hidden layer here. I think we're just going with this many parameters. We will see. And this is stochastic gradient descent. So it defines a classifier. Now we define the random state here. We're just going to use default values for all the learning parameters. And the random state is to make sure that even though you have pseudo-random numbers, they're always going to be exactly the same because you specified the seed to be 42. We do that a lot just to make sure students will get exactly the same answer as me. In the real world, you'd probably just seed the random number generator from something like a clock to get more pseudo-random numbers. So here it is, training. Now I didn't even tell it how many epochs to train. So the default, I think, is to use early stopping. And what that means is you keep training as long as the loss is going down, and the first time the loss goes up, you stop because you figure, well, that must be the bottom. That's one simple way to know when to stop. And see, the loss is still going down, and now the loss is still going down, and now the loss went up from 81.70 to 81.76. So as soon as it starts going up, then you quit. You say, well, I appear to have hit the bottom. And this loss is just some kind of measure of how many of them were right and how many of them are wrong. So it converged, that's what they call it, after 30 seconds and 239 epochs. And here's some predictions. I predicted 5, 0, and 4. And this was true, it's a 5, and the next two are predicted false, that they're not a 5, so the first 3 predictions are correct. And now we can measure accuracy. We're going to do it with cross-validation, so we're going to split the training data into 3 folds, train it 3 times, each time training it on 2/3 of the data, and evaluating the accuracy using the excluded fold. So that's what it will do for cross-validation. This is a way to evaluate how good your model is. So it should take some time. It's going to have to do 3 whole cycles of training. And when it's done, we're going to get accuracy measures of 95, 96, and 96. That's what I got here. Here's the accuracy, 95, 96, and 96. And then another way to specify the accuracy is a confusion matrix, which gives you a chart of all the various ways you can be right and wrong, which is more detailed than just an overall percentage right and wrong. So I'll put in this code while that is still running. And I think I need to let it finish. There, it's done. So here's the 95, 96, 96. And this is going to give me, scoring the accuracy, it's going to give me the chart. And looks like I'm repeating the training. I'm not sure that was necessary. But anyway, you'll get this chart. So this is not 5, correctly marked as not 5, I think. Yeah, the first row is the non-5 images. So the not 5 images are mostly correctly identified as not 5, but 687 were falsely called 5 when they weren't 5. And the second row is the 5s. And as you can see, we got 3,500 of them right and 1,800 of them wrong. So we missed almost a third of the 5s. And we had false negatives something like a third of the time, where a 5 was not detected as a 5. And we had false positives only about 1% of the time, where a non-5 was incorrectly identified as a 5. So that's a more detailed analysis of the accuracy of our activity here. And there are various numbers you can use. Precision is true positives over the total, and that's going to be 80%. And the recall is true positives over true positives plus false negatives, called the sensitivity, and that's 65%. And then there's this thing called an F1 score that combines the two, and it will only be near 1 if both precision and recall are near 1. So these are just various ways to measure the accuracy of a model. And you have a precision recall trade-off. What happens is when you're done, you have a neuron, and the neuron is supposed to have a large signal for a 5 and a small signal for a not 5, and you can adjust the threshold. So if you set the threshold low, then it will have a high probability of reporting true, and therefore you will have more false positives but less false negatives. Or you can go the other way, set the criterion very high, so it's only going to call it true if it's very confident that it's a 5. So you'll have less false negatives, less false positives, but more false negatives. So you can adjust this to meet whatever the best criteria are for your situation. And you can view the raw neuron output. And you'll see it here, just a numerical output. It might be negative and might be positive. And you can change the threshold values. And I think I don't need to do the intermediate ones. I think I can skip right to this one. Let me see if it works. I think those ones in between were just printing out things that we didn't need to remember. And this will give you the threshold. Okay, it looks like cross-val predict. I did need one of those things in the middle. I'm not going to bother doing it. I'll just, if you do it right, then you get this graph. here's precision and recall, and here's the threshold. So this is the same thing. I remember seeing this in all the Security Plus kind of classes about biometric identifiers. You can adjust the sensitivity, and you can either go to accepting almost everything, in which case you'll have almost no false negatives but some false positives, or you can be very picky, in which case you'll have almost no false negatives but some false positives that were positive but they weren't high enough to be detected. And up here it gets noisy because the denominator is getting near zero. So that's the game. And then you can move to multi-class classification. And the way this works, it's kind of insane. The only thing you can really make is a binary classifier, so you just make a bunch of them. There's two techniques. There's one versus the rest and one versus one. And one versus one will make 45 classifiers, which means compare 0 to 1, compare 0 to 2, compare 0 to 3, and so on. So there are 45 possible pairs, and it does all 45 of them to come up with a combined score from the 45 classifiers of how likely it is that the thing is a 0 or a 1 or a 2 or so on. This is something I was surprised when I learned it in this class. Many real machine learning projects involve making a lot of machine learning models, like even hundreds or thousands, and combining the output. It's hard to believe that's the best way to do it, but that's really what happens. And so here are, I think, some sample outputs. Yeah, the first column is the right answer, and the second column is true if it was correct and false if it was not. And it prints only the wrong ones. So it was wrong 3 times, and one of them was image 80. And so here is the right answer is 9. Here is the raw score for each of the categories, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And as you can see, the largest value is 0. A 9 only got a rating of 6, so the right answer was 6. It thinks it's more likely to be an 8 and even more likely to be a 0. So that's a pretty scrawled number. And here's one that should have been a 1, which got a score of 8, but as you can see, 2 got a score of 9. So those are when it gets it wrong. It only got 3 of them wrong out of, I think, the first 100, but those are the ones that it got wrong. And you can use one versus the rest, which is another way to do it, and then you only need 10 classifiers, like we made before, 5 or not 5, 0 or not 0, 1 or not 1. It's another way to do it. And if you do that, this one, in this case, only gets 2 of the first 100 wrong. And notice 48 and 80 are the ones that got wrong here, and the 2 this one got wrong are 48 and 80. So as you would expect, it's going to be particularly distorted or scrawled images that confuse both models. And we can train a model with stochastic gradient descent in multi-class classification. And I'm not quite sure. Oh, this is a way to do it where you have, I think we're using just one model, although I'm not quite sure. Anyway, if you do that one, you get another one of these outputs. And here we're going to do overfitting. You can, there, much worse at the test set. So here, when you train it, it's going to get only 5 of the first 500 images wrong. And that's because this model has a lot of parameters. But when you run it on the test set, it gets 91 errors in the first 500, so that's overfitting. You're getting, 20 times more errors on the test set than you got on the training set. So your model is not as good as you think it is. It fits the training data, but by overfitting. All right. And so that's, now you can actually get down here and plot the 10 by 10 confusion matrix. So these are zeros that are really 0, correctly predicted as zeros, and these are 1s correctly predicted as 1s. And as you can see, mostly it works, but here's the errors, and you can now see exactly what type of errors there are. Like, it's very likely to have a 1 that's misinterpreted as an 8, and it's very likely to have a 7 misinterpreted as a 9, and so on. But there are other things that are not very likely, like a 5 being interpreted as a 0, or as a 1, I mean. So
Can you talk about what the use would be of a model like this that had any inaccuracies at all?
Well, everything always has some inaccuracies. Even humans judging it will have inaccuracies. So this is useful, for processing handwritten data, which is a problem a lot of people have. Like you have medical records or people have been recording blood pressures and stuff with a pen, and you want to digitize that. So use a model like this. The same thing for X-ray images, right? They've trained models to look at X-rays and decide if you have lung cancer or something, and it turns out they're more accurate than humans. Neither of them are all that accurate. But they were able to train it on cases where you later found out whether they really had it. And I think like humans were like 85% accurate, and the machine learning models can get up to like 89%.
So the practitioners just have to be made aware that it might not be accurate.
Yes, everything has flaws, and here you get a complete printout of exactly what kind of flaws were made. And so you could decide now if you care about some of these errors more than others. And in a case like a medical condition, you might say, I want a model that whenever it says I want a model that has no false negatives. So I'd be happy if it flags some people that don't have cancer as having cancer, so we subject them to more tests. I'd rather have that than having it say no when they really do. That's the kind of thing you'd use this to guide you. You might want to adjust your model to remove certain types of errors that really are unacceptable. But I mean, nothing's ever going to be perfect. And so that's the goal here. So you get to see how classification works. And that's the point of 105. I'm going to stop this recording.